Okay, let's talk about the moment of inertia. The moment of inertia, we use the letter I, and it is basically a rotational version of mass. If mass is our resistance to motion, meaning changing our direction and or speed, and a force is required to do that, then the moment of inertia is our rotational inertia, which is our resistance to rotating, and a torque is required to do that. Again, these two are absolutely parallel to each other. If you have a net force, you're going to accelerate, meaning change your speed and or change your direction. If you have a net torque, then you're going to get an alpha, which is the rate at which you change your omega, meaning your spin rate. You're going to start to spin or stop spinning. And the rate, the proportionality constant, well, force is mass, right? It's your resistance to accelerate. And in rotational sense, it's I. So the moment of inertia of an object or of a system is its resistance to turn. So we have all these that we can memorize. It's just nice, like the moment of inertia of a disk. We can prove later that it's 1/2 mr squared. The moment of inertia of a hoop is mr squared. The moment of inertia of like a point particle, when we say point particle, we mean an object where we're considering all of the mass located at the exact same spot, is just mr squared. The moment of inertia of a sphere, so like a ball rolling down a ramp or a ball rolling across the ground, is 2/5 mr squared. And then we have the moment of inertia of a board is 1/12 ml squared. The moment of inertia of a board pivoted in a different spot is 1/3 ml squared. Okay, and so for this one, this is the pivot in the center, and for this one, this is where the pivot is at the end. And you can imagine if I take a board and I pivot it in the center and I try to rotate this thing, it's going to be much easier to rotate when the pivot's at the center than if I put it here. Again, those two, it's the same board with the same mass and the same length. And this formula would suggest that this version is 4 times more difficult to rotate than this one is. And I think you can imagine that, look how much more mass and look how much further it is away in this version. All of this over here, all of those little pieces of the board are much more further away than any of these are, right? The furthest this is away is L/2. And so this is similar to that, and then all of that is much different. And again, those are the formulas. These 6 are the things you probably should commit to memory: disk, hoop, point particle, sphere, board at the center, and board at the end. Okay, and again, those are all these different objects. So what happens if we take a disk and we pivot it somewhere else? So let's put the pivot not at the center and not at the edge, but let's put it halfway. And so it would seem like then the moment of inertia should increase. It would be more difficult to rotate this particular disk there than if the pivot was there. And so what we're going to do, we're going to use the parallel axis theorem. The parallel axis theorem says that the moment of inertia I is equal to I naught plus md squared. Again, this is the parallel axis theorem. It's very helpful when we move the pivot away from the center of mass. And what this says is that the new moment of inertia is the original moment pivoted in the center plus md squared, where d represents the distance you've moved the pivot. In this particular example, the original moment of inertia of a disk is 1/2 mr squared plus md squared. Well, in this case, I've moved the pivot from the center to a distance of r/2 squared. This is 1/2, this is 1/4. I end up saying that they get 3/4 mr squared for a disk pivoted in there. Again, I can put this pivot wherever I want now, and I can use the parallel axis theorem to find this. I can actually use the parallel axis theorem to derive the 1/3 ml squared for a board. The parallel axis theorem says that this is true for a board, and if I take a board centered, I I get 1/12 ml squared. And then if I take the pivot, and I take it from the center, and I move it all the way to the end, then D should be L over 2. And if you take 1/12 ml squared plus 1/4 ml squared, 1/4 plus 1/12 is in fact 1/3 ml squared. So what we did is we derived this guy from this guy using the parallel access theorem. And again, we don't have to put it on the end. I can put it anywhere I want on this board, and as long as I know the distance I've moved the pivot and I know the moment of inertia of the center of mass, then I can find the new moment of inertia. And as you can see, md squared is always a positive term. It's always going to grow the moment of inertia. Okay, and it's certainly moving the pivot from the center of mass is increasing then on average the distance all the mass is from the pivot, which would make it more difficult to rotate, which is an increase in I. Again, I would commit these 6 to memory. You're going to use them enough in problems. And one of the things I guess I want to say is that, you know, we almost always use 1/2 mr squared, because anything that's a pulley in our problems, we're going to claim that that's equal to a disk. Okay, so we have the 6, and then we do have the parallel access theorem, and then there are 2 more really pieces that I want to talk about. Piece number 1 is, how do you find the total I of like an extended object or a more of a complex object? And what I want you to know is that the real definition of I is that it's the summation of all these mr squared things. Now again, for the disk, we're going to use calculus in a second to show you how this is, but really the total moment is the summation of everyone's contribution. And again, some of these formulas we already have memorized. So let's just take like a merry-go-round, which is a disk, and then let's put a person on the edge of it. Okay, and so, well, what's the difficulty in spinning that? What's its moment of inertia? Well, its moment of inertia is the summation of everything. So the total moment of inertia is just like the merry-go-round's moment of inertia plus the person's moment of inertia. The merry-go-round we'll consider as a disk, so it's a 1/2 mr squared, and then the person is a point particle. And you remember, a point particle is just mr squared, and since he's on the edge, or she's on the edge, that's just an mr squared. And again, these m's aren't different. This m is the mass of the disk, the merry-go-round, and this mass is the mass of the person. But the total moment of this is just the summation. If I put another person on, so let's say I have a person standing there, there's the center, and I have another person that climbs on right there, then I would just have to add another term, a different mass, and if I put them halfway in between the center and the edge, then I would add that. And again, that would be like person 2, person 1, merry-go-round, the moment of inertia, meaning the difficulties to start or stop spinning this thing, is the summation of all those pieces. The other thing we want to look at, again, so we have the moment of inertia of all our objects. We have the moment of inertia if we move the pivot using the parallel access theorem. And then we have the moment of inertia of a system of things, which is the summation of all the pieces. And again, all the pieces, sometimes they're formulas, like a disk or a hoop or a ball or a board, and sometimes they're just point particles where it's just simply mr squared, where r represents the distance that object is from the pivot. The last thing we want to do is actually the calculus. And so the calculus, we'll go algebra first. The algebra says that the moment of inertia is the summation of all the mi ri squares. But in calculus, that's the same thing as summing up all the dm's at their r squares. And again, this is identical, the calculus version, to the algebra. And so what it would look at is you would need to take all the pieces, their contributions at r squared. So let's do the board. All right, we already know the answer. This answer has to be 1/3. And so if we put the pivot right here, we need to break this extended object up into an infinitely number of really, really small pieces. So each piece of this board then we consider some dm. And each dm is a different distance, meaning r, from the pivot. So all of these dm's, you break them up in a whole bunch of dm's here. Right? This is just one particular dm. But we're breaking up into an infinite number of things, very similar to LRAM and RRAM when you start talking about like calculus. and finding area. That particular dm is a certain r away, and it's a different r than everything else. It plays a certain role, and what we need to do is sum up all those contributions to find the moment of inertia of that system. This gets a little confusing at times, but dm, we need to be able to relate it to dr, meaning if dm represents the mass of that, we need to find the thickness of that. But if we take m and divide by L, we get a mass density. Now, it's not mass per unit volume, it's mass per length. Kilograms per meter. It's a linear mass density. So if we take m over L, that's like kilograms per meter, and we multiply by dr, dr being the actual width of this little segment, then we actually get the mass. Again, dm is equal to m over L times dr. Kilograms per meter times number of meters of that width gives us the kilograms of that width. We're going to integrate dm, so we're going to put in dm. Again, I just substituted m over L dr in for dm right there. And then what are we going to integrate from? Well, what are we letting r vary from? Well, the dm's that are really close to here are at 0, and then we're going to let r, vary all the way until L, the total length. Again, some of the dm's are really far away, some of the dm's are in the middle, and some dm's are really close, and that's why we let r vary from 0 to L. M and L are just constants, so they're allowed to be pulled outside of the integral. I'm going to rewrite this in the conventional way such that it's r squared dr. This is a polynomial, so I'm just going to do power rule. Power rule says increase the power by 1, divide by the new power, and then I'm going to evaluate it from 0 to L. So that's me plugging in L, so I get L cubed over 3 minus plugging in 0, but then I just get 0, right? Because I get 0 cubed over 3. L cubed over L is L squared, and look, you have m L squared over 3, and that's the same thing as 1/3 ml squared. And again, this is the exact same thing we got when we did the parallel axis theorem. This is the moment of inertia of a board of mass m, length L, pivoted at the end. And this is the calculus way. Again, algebraically, it's fine. We're summing up all the contributions, and the calculus is we use an integral for that. All right, the last one I want to show you is the same thing, except it's the calculus version of doing a disk. So we take this disk, and we need to break it up. And again, the disk has mass here, mass here, mass here, all different distances. Well, the one thing you're going to realize is that you can break this thing up into rings. Each ring has its own mass. Again, let's just review. The moment of inertia is the summation of dm times r squared. Dm, we'll call that the mass of each ring. And so each ring doesn't have necessarily a length we want to talk about, it has an area we want to talk about. So let's take m and divide by pi big R squared. That's kilograms per square meter. That's the area mass density of the entire disk. And we're going to multiply by the area of each ring. If you think of the ring as a rectangle, again, snip one of these rings, then unravel it. This distance is 2 pi r, the circumference of the ring, and this is the thickness of the ring, which is dr. So if you take, this is the area of each ring times the number of kilograms per area, gives you then the kilograms of each ring, which is dm. So let's take dm and make a substitution. So I have m over pi r squared times 2 pi r dr times r squared. These pi's are going to cancel, and that's convenient. And then I'm going to take m, the 2, and the r squared outside the integral, 2m capital R squared, because those are constants. And then I leave in r times r squared is r cubed dr. And we're going to evaluate this from 0 to capital R. Remember, what are we letting r vary from? We're going to let r vary from 0 to We're going to sum up all the rings until we get to capital R. So we get 2m over r squared, and then the integral is r to the 4th over 4. Evaluate from 0 to r. So we get 2m over r squared times big R to the 4th over 4, and then when you plug in 0, you get 0, so this is just, again, subtracting 0. If you look at this, this is 2 force is 1/2 m. R to the 4th over r squared is r squared, and again, it's the exact same thing as what I told you we memorized at the beginning. Again, if you look at the beginning, the moment of inertia of a disk was 1/2 mr squared. A board was 1/12. A board pivot on the end is 1/3. And that's exactly what the calculus gave us. Again, you might have to review the calculus a little bit, and it's not the easiest thing, but just remember that the moment of inertia is the summation of all the dm and r squares. Algebraically, it would look like this, but that's the same thing as the calculus. Okay? So, in review, again, our first sheet that we looked at gave you this. It said disk, hoop, point, sphere, and then 2 different boards. You wouldn't have to memorize the end of the board because we derived it, but it's probably nice. You're going to use it enough. We said that forces cause accelerations and torques cause alphas. And how big alpha is, well, what are you trying to rotate? If the bigger the thing is to rotate, the bigger the moment of inertia, the smaller the alpha will be based on the torque. Just like the more massive an object is, the smaller the acceleration will be based on a constant force. The parallel axis theorem is really helpful. It allows us to find the moment of inertia of something if we move the pivot from the center mass. Move it from the center board to the end of the board, a center of a disk to the middle of the disk, or the edge of the disk. And we really can do that for any of those objects.